So today I'm going to show you an easy way to find out equivalent hydrogens, and this is known as homotopic and heterotopic hydrogen atoms. So what this basically means is that if you have a let's say you have this molecule, and what you want to do is you want to find out how many different hydrogens are there for your proton NMR. So what you'll have to do is basically, you can check for the symmetry, which is basically right here. And so this is one way to find out how many different kinds of hydrogens there are. So you see, like, there's one right here, and there's another one right here, and another one right here. And what you have to notice is that this is a free rotation bond, so it might not look like it's symmetrical, but it actually is, because it can rotate. So when it rotates, by using your Newman projections, it will become like this. It's the same thing. So we have 1, 2, 3, 4, 1, 2, 3, 4, just as an easier way to present this. And you can see the symmetry straightforward in this example. But now I'm going to teach you another way, and this way is really easy, I feel like, than just doing symmetry, because symmetry is kind of hard sometimes and you can miss it. But by this way you can just be like, oh, this is the answer. And I hope it works out for you. So I'm just going to do the same molecule again. So it's like butane. Now what I'm going to do is I'm going to label all the hydrogens in here. Actually, I'm going to use a red marker. So there's a hydrogen right here. So 3 hydrogens right here. 2 right here. And I think this is really easy, like if you label the hydrogens beforehand, because then you can see. Because what I tend to do is like miss some hydrogens by like overlooking them, and then I get it wrong, so it's like easy points to not miss. So now what I'm going to do is I'm going to see if all of these are equivalent hydrogens or not, so we can see how many NMR signals there are. I'm going to draw this again. This is the same thing. So now we're going to start with this hydrogen right here, and I'm going to use a red marker again, but I'm just going to choose one of the hydrogens randomly and replace it with a chlorine. You can replace it with any molecule, but I just like chlorine, so I'm going to use that. So you can do any of these also, so don't worry about it. So now what you do is you name it. So I'm going to name this 1-chloro-butane, right? And now I'm going to take this carbon right here, and I'm just going to replace one of them with chlorine. Oh, you guys can't see it. Okay, I hope you saw this one. So I'm going to replace this one with chlorine and name it. So 2-chlorobutane. Okay, cool. I'm going to actually number these. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 4. Okay, now I'm going to take the 3rd carbon and write Cl. So even though this is the 3rd carbon, as you know, according to IUPAC, we have to start with the we have to start numbering so the substudent can get the lowest number. So in this case, it would be 2-chlorobutane. And now the last carbon, oops, let's see that, okay. So the last one will be right here, chlorine, and additionally, so it's 1-chlorobutane. So now what you'll see is like this naming is supposed to tell you the difference between them in their environment. So as you can see, these two have the same naming right here. So that means that the hydrogens are equivalent. And these two have the same naming. So that means that they're equivalent. So in total, we have 2 different signals. Because we have 2 different namings. So that's basically what homotopic means. And this is like a better method, in my opinion, to use. And you can also double check it when you're using the symmetric method or something. Okay, I hope this helps.